Hello, my name is Hugo and I present about the paper a 2.4 GHz wireless temperature sensor with 0.93 Celsius degree precision for IoT applications, designed in 130 nanometer CMOS technology. The summary will cover the main topics of the paper's abstract, the problem statement. The increasing number of the devices connected to the IoT demands efficient and scalable solutions. IoT devices require compact and energy-efficient components to meet portability and cost constraints. Accurate and reliable temperature sensors are crucial for multi-monitoring systems in IoT applications, and the use of open-source tools can promote accessibility and democratization of IC design. So this paper proposed the development of a compact and energy-efficient temperature sensor with wireless communication for IoT applications. About the contribution, this paper just uses open-source tools and open PDKs. This sensor has a modular architecture with customizable blocks, linear temperature voltage relationship, wireless communication in the 2.4 GHz ISM band, low power consumption, only 1.6 milliwatts, small area, 0.028 square millimeters, and high accuracy with maximum area of 0.93 Celsius degree, and this sensor was compared to other sensors in the state of art. About the open source design, here is the flow used, just open source tools and the Skywater 130 nanometer open PDK and some post-processing with Python. The sensor is composed by the PTAT, the buffer, to generate the DC signal referring to the temperature. This DC signal is converted to a digital signal by this sigma delta modulator, and this digital signal is converted to a RF signal with the ASK modulator. The first result is the linear temperature voltage relationship. As we can see in this temperature sweep, this green line is the output of the buffer, which was compared to this blue line here. And even with a maximum error of 1 Celsius degree, the sensor achieved this temperature range. So this simulation was done with FF and SS corners to analyze variation in the fabrication process. So even with this variation, the sensor achieved this temperature range. The second result is about the wireless communication. As we increase the temperature, the sigma delta changes the patterns of the pulses, as we can see here. And when the pulses change from 0 to 1 and from 1 to 0, the RF block, the ASK modulator, sends an RF signal, which is depicted in this FFT here. So the fundamental component of 2.4 GHz ISM is included in this range here. Low power consumption. As we can see, the ASK modulator, the RF part, consumes 87% of the energy. Here is the layout of the sensor. This table shows the comparison of this paper with other temperature sensors found in state of art. So all these sensors have just the analog and the digital blocks. So this paper has the RF block also. So the RF block, the ASK modulator, represents 75% of the total area and consumes 87% of the total energy. Without the RF block, the device showed a smaller area than all the other sensors and lower energy consumption than 16 and 19. And with RF block, this work presented a smaller area than 16, 18, 19, and 21, as well as lower consumption than 16. And the main conclusion are The complete circuit consumes only 1.6 milliwatts and has an area of 0.028 square millimeters, smaller than the most of the other compared sensors. Its maximum error was 0.93 Celsius degree for a temperature range between 12 and 144 Celsius degree, which is lower than all the analyzed circuits. The proposed temperature sensor demonstrates its viability and relevance for IoT applications due to its accurate temperature measurement, efficient wireless communication, low power consumption, small size, and high accuracy. The use of open source tools and modular design further enhances its accessibility and customization potential. And here is the references.